Let's look at this predicate. Here we have the predicate P of n, which is 1 plus 3 plus 5 plus all the way up to 2n minus 1. And we want to show that this is equal to n square. So we can try to verify this for some values of n. So if I take P of 1, then the last term will be 2 times 1 minus 1, and this is equal to 1. That means the last term is going to be 1. That means I have just one term, and 1 is equal to 1 square. If I look at P of 2, then I will have 1 plus 3, that is equal to 4, which is 2 square. P of 3 is 3 square. We can continue. I would ask you to check the math. P of 9 is 1 plus 3 plus 5 up to 17. Yes, that is equal to 9 square. Now we can do this for many possible integers, and we will find that this result is indeed true. But that still doesn't mean that it is true for all integers n, because we would have verified only a few of them, and we want to conclude this for all n. So the goal of induction is to be able to show that the statement for all n, P of n is true. So suppose we want to assume that without verifying this result is true, namely P of 21 is true, that is 1 plus 3 plus 5 all the way up to 41 is equal to 21 square. Now we are assuming this, we are not going to prove it per se, we are not going to use any calculator to see if this is actually true. We are going to assume this result. Remember that this is just an assumption. Our goal now is to show that P of 22 is true by simply assuming P21 is true. Another way of thinking about this is we want to prove P of 21 implies P of 22. So this is our assumption. This is our conclusion. This is what we want to do. We are not going to prove P of 21. We are going to assume P of 21, and then we are going to try to prove P of 22 is true. So let's look at what we can do. So the question we have is P of 22 this statement, is this true? Now what we can observe is inside this I have this first part of the expression. Let me use a different color. This is basically same as this expression, which we know is equal to 21 square, because that's something we are assuming. So this is P of 21, and this is equal to 21 square, and now we are adding 43, and we are checking if this number is equal to 22 square. So now the question boils down to, is 21 square plus 43 is same as 22 square? We can rewrite 21 square slightly differently as 22 minus 1 whole square, and we can do some math, and we can see that indeed this result is true. Now the thing here is, what we did was we assumed P of 21 is true. We did not prove it, and based on this assumption we showed that P of 22 is true. Think about this slide a little bit. If there are questions, I would suggest first review the slide one more time. If there are still more questions, uh, you can use Piazza to discuss this as well. Now what we are going to do is we are going to see how general was our method. So we showed P of 21 implies P of 22, but what of P of 22 implies P of 23? What of P of 7 implies P of 8? Could we generalize this so that instead of 21 as a specific number, we could do something where we would be able to do a lot of these proofs all at once? So we are going to replace 21 by some placeholder k. So k is just an integer. We are not going to make any assumptions about it other than the fact that it's a positive integer. Now we are going to assume that P of k is true for some specific k. We don't really care what that k is. And our goal is to show that P of k plus 1 is true, which is this expression over here. So essentially what we are trying to prove is P of k implies P of k plus 1. And note that while we are doing this, we are not going to assume k to be a specific value. So we are not going to say, well, let k be 7 or let k be 21. We are not going to do that. We are going to let k be any arbitrary value that it can take, any arbitrary integer value it can take. So let's see what we can do. We are going to do exactly like what we did before, but instead of 21, we are going to have this k over here. So what we can observe is, just like what we did in case of 21 and 22, I can write P of k plus 1. I can take the first few terms, leave out the last one, and now this expression is same as the expression that we assumed over here. So we can replace this by P of k. We can replace this with k square because that's something we're assuming. And now I have k square plus 2k plus 1, and that is in fact is equal to k plus 1 square. Note that this is true for any value of k. And that's exactly what we are trying to do. And when we do that, we have concluded that the statement is true for k plus 1. Let's see what we have accomplished so far. We proved this for any value of k that was an integer. That means we showed P of 1 implies P of 2, P of 2 implies P of 3, P of 3 implies P of 4, blah blah blah. P of 6 implies P of 7, P of 19 implies P of 20, and so on and so forth. At this point, we don't know whether P of 6 is true, P of 17 is true, P of 19 is true. All that we know is if P of 6 is true, then P of 7 is true. If P of 7 is true, P of 8 is true. So all we need to do at this stage to show that the statement is true for any value of n is to show that P of 1 is true. If we show that P of 1 is true, then from the first statement I will get P of 2 is true. From the second one I will get P of 3 is true. From the next one I'll get P of 4 is true. From the next one I'll get P of 5 is true, and so on and so forth. So no matter which value of n I choose, this statement will be true. Once again, we have reached the check before you go ahead slide. I want you to understand a few important properties of interest from this module. First, we showed that in the inductive step, Pk implies Pk plus 1. The important requirement here was k was an arbitrary integer. We did not make any assumptions like k was 2, k was 5. We did not make such assumptions. And this is very important. You cannot make this assumption when you are doing this proof. Now, because we did not make this assumption, when we proved Pk implies Pk plus 1, we actually proved this for any arbitrary Pk, and that means we proved P1 implies P2, P2 implies P3, and so on and so forth. So essentially we are proving infinitely many things when we are proving Pk implies Pk plus 1 because we are not assuming anything about what k is. Note that the term Pk and Pn looks essentially the same. Pk is the term that we used in our inductive step. Pn was the statement originally. They look essentially the same, and therefore some students confuse between them, as in thinking, are you assuming what was already are you assuming what was asked to be proved? Now, some of you, especially those who have been used to induction before or may have learned induction from different place, you may actually see the inductive step to be of the form Pn implies Pn plus 1. That's okay to do because recall that k is just an arbitrary integer, and just like a variable in a program, we could call it whatever we want. But some students get confused between this Pn implies Pn plus 1 and the statement we are trying to prove, which is for all n P of n. Because of that, if you are using induction for the first time, I would discourage you from doing that. But if you do it, for example, on an exam, it would be fine. It's just that some of you will find using this type of structure for inductive step a little bit confusing.